All right, so today we are going to be doing section 3.4, zeros of polynomials. And so these are the topics. We're going to look at the fundamental theorem of algebra quickly and what the rational root test tells us, Descartes' rule of signs, upper and lower bounds, and then just a little quick thing about complex conjugates. The first four things, and especially the three middle things really, those are going to be to help us factor and find zeros of polynomials. And so anyway, let's just jump into it. So the first thing, the fundamental theorem of algebra. There's not much to this. So here's what it says formally. Every polynomial p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... and so on, with complex coefficients has at least one complex zero. And so that's the key, is there's going to be at least one solution to every polynomial function. That's all it's saying. Now, what follows from that is a little slightly more interesting. Granted, it's only slightly. But it says what follows is that a polynomial function of degree n will have at most n unique zeros. It can have less, but it will have at least n unique zeros. So a fifth degree polynomial is going to have at most 5 zeros. A seventh degree polynomial is going to have at most 7. So it tells us a little bit about the zeros. And that's all we're going to do with that. Now we start getting into some more useful stuff. So the rational root test, that says if a polynomial, and again it's going through this definition of a polynomial, has integer coefficients, then every rational zero of p is of the form p over q, where p is a factor of the constant, q is a factor of the leading coefficient. Up until now, when you guys have been doing synthetic division to factor polynomials, you've always been given a starting point. What if you're not given that starting point? You need to find it yourself. And this gives you a way to narrow down the possibilities for that starting point. Let's just take a quick look at an example of how you can use this. So this one's already worked out for us. But it says list the possible rational zeros of the polynomial, and then it gives us this polynomial. Now, according to the rational root theorem, we look at just the leading coefficient and the constant term. And just look at the factors of those. So the factors of 4 are 1, 2, and 4. The factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, 36. Oof. And according to the rational root theorem, it says that any possible rational root is going to be the form factors of the constant over factors of the leading coefficient. So what does that mean? That means that we could have 1 over 1, 1 over 2, 1 over 4, or 2 over 1, 2 over 2, 2 over 4, or 3 over 1, 3 over 2, 3 over 4, and so on. And that's what I've done here. 1 over 1, 1 over 2, 1 over 4, 2 over 1, 2 over 2, 2 over 4, 3 over 1, 3 over 2, 3 over 4. Oh my goodness, they're all right here. And the one thing that's not clear from there, but factors can be positive or negative, so every one of these is positive or negative. Oh, we still have a lot of possibilities here. But at least we know don't try something like 1/5, or don't try 5. It's not in this list, so it's not going to work. We do have some duplicates that popped up here, so that's nice. If we look at this second row, any of these fractions that reduce, they're already up there. 2 over 2 is the same thing as 1 over 1. And 4 over 2 is the same thing as 2 over 1. And 6 over 2 is the same thing as 3 over 1, and so on. So all of these that I didn't highlight, that's because they're already duplicated. 12 over 4 is the same thing as 3. 6 over 4 is the same thing as 3 over 2. So I just ignored the ones that ended up being duplicates, and right here are all the possible rational zeros of that given polynomial. So 1, 2, 3, 4, 6, 9, 12, 18, 36, 1 half, 3 halves, 9 halves, 1 fourth, 3 fourths, 9 fourths, and the negative of all of those. So there's still a lot of possibilities, but this is a lot less than infinite, so we like that. It helps narrow down our list a little bit. But this is only so useful, and it depends on the problem. Sometimes this is really useful, but sometimes you get a long list still like this. It's like, oh my gosh, still, what do we do? So there's going to be some other things too that we're going to do. So we're going to go through like all the different theorems, and then we're going to look at how we can put them all together to help us actually find zeros of a polynomial. So this is one thing, is the rational root theorem. There's something else called Descartes' rule of signs. So let's see what Descartes' rule of signs says. Let's read the formal, and then we'll look at how we put it into practice. So the number of positive real zeros of p of x is either equal to the number of variations in sign in p of x, or is less than that by an even whole number. And then the number of negative real zeros of p of x either is equal to the number of variations in sign of p of negative x, or is less than that by an even whole number. This makes it sound a lot more confusing than it is. Let's take a look. So, describe the real zeros of f of x using Descartes' rule of signs, and here's f of x. So, actually let me bring this down a little bit. We're going to look for variations in sign of p of x. We're dealing with f of x, but let's look for variations in sign. Sign changes. Sign changes in the coefficients though. So first I just make a note of the positive and negative. So like 3 is positive, then we got -4, and then we got -5, and then we got 3, and then we got 2, and then we got a -7, and then we get a 10. So I'm just looking at the signs. And then where was there a sign change? I changed from positive to negative, then I changed from negative to positive, then positive to negative, and negative to positive. So I'm counting 1, 2, 3, 4 sign changes. So what does that mean? Back up here. The number of possible real zeros of p of x either is equal to the number of variations in sign. So there were 4 sign changes. The possible number of positive real zeros of f of x are 4 because of 4 sign changes, or less than that by an even whole number. Basically just keep subtracting 2 until you can't anymore. So 4 minus 2 is 2. 2 minus 2 is 0. 0 minus 2 would be negative. That can't have a negative possible zeros, so I stop there. So I know the number of positive real zeros of this polynomial, there are either 4, 2, or none. And now I know. I do the same exact thing for the negatives, except I'm just going to plug in a negative x first. Remember when you raise a negative to an odd power, it's going to be negative, so it's going to change the sign. So this 3 is going to become a -3. But a negative to an even power is positive, so we won't change the sign. So basically, if there was an odd exponent, change the sign. If there's an even exponent, you won't change the sign, just because of what happens when you plug in the negative x. So even exponent, I keep the sign the same. Odd exponent, I change the sign. Even exponent, keep the sign. I think I said odd. Anyway, even exponent, keep the sign. Odd exponent, change the sign. And this is really an even exponent, keep the sign. So I had a negative, 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 positive, positive, positive. There was only one sign change here. So as far as the possible number of negative real zeros, there are only 1. And if I subtract by 2, because remember, less than that by an even whole number, if I take 1 and subtract 2, I'm going to be negative. So the possible number of negative real zeros of f of x is 1. That means I know there has to be 1 negative real zero, and that's it. If I find it, don't try any more negatives. Honestly, Descartes' rule of signs, some people use it a lot more. I don't use it that much. There are some times, though, when it comes in handy. Sometimes this is a little more work than I feel like it's worth, but when you're doing these things by hand, I'll show you as we go through an example, but that's the idea. Our last one is the upper and lower bounds. So let's just look at what this is. This one's better to explain in practice, so we're just going to look at it and then we're going to start doing some examples. So the upper and lower bounds says this: if we divide p of x by x minus b using synthetic division, and if the row that contains the quotient, that's the bottom row, remember, and the remainder has no negative entry. No negative entry, remember, that means positive or 0. So if it contains no negative entry, then B is an upper bound for the real zeros of P. Now what does that mean if you're an upper bound? That means there are no zeros above that. So don't pick anything bigger, because you know there won't be any. If we divide P of x by x minus a, where a is a negative number, using synthetic division, and if the row that contains the quotient and remainder has entries that are alternately non-positive and non-negative, then a is a lower bound for the real zeros of P. So like I said, these are a little easier to explain when we put in practice. So now let's just see how we would use these things. Let's just quickly remind ourselves. There's 3 key things that we just did. So the first thing, the rational roots theorem. Any possible rational root is always going to be of this form. Factors of the constant over factors of the leading coefficient. Don't try anything else, it won't be worth it. It's not going to work. Descartes' rule of signs. You look for sign changes in f of x for the positive real zeros, and you look for sign changes in f of negative x for the negative real zeros. And then upper and lower bounds, if you plug in a positive and you get all non-negatives in the bottom, then you have an upper bound. If you plug in a negative and the entries in the bottom row are alternately non-positive and non-negative, then you have a lower bound. Those are the things we're looking for. And it's not that bad when you see how to actually put this in practice. So let's take a look at this first one. Fully factor this. So if I look at that, the first thing I notice is there's no sign changes. Now remember, let's just quickly go back to Descartes' rule of signs here. According to Descartes' rule of signs, the number of positive real zeros is equal to the number of sign changes in P of x, or less than that by an even whole number. We don't have any sign changes. That means no sign changes, there's no positive real zeros. Don't try any positive numbers. Just skip that and go on. So I'm going to go ahead and set up for synthetic division here. We got 1, 5, 7, 3. Normally I would start with a positive 1, but I already know it's not going to work. I'm going to start with a negative 1. A negative 1, multiply by negative 1, add, multiply by negative 1. Oh, look at that. I got lucky. I found one. So it says fully factor. If negative 1 is a 0, then the factor is x plus 1. And then remember that these numbers in the bottom row are your coefficients for your other factor. And then this guy, he factors further. What 2 numbers add up to 4 but multiply to 3? And it's 1 and 3. And you could write your answer like that, or write it like this. Either one. That doesn't matter. There you go. Look at that. We factored that cubic without a whole lot of work. Now, not everything's going to be that easy, but that was a good warm-up. Okay, let's try another one. Okay, so let's just take a look at how we would approach this one. Now, like I said, Descartes' rule of signs, I don't think about it too much, but I do look, like right now I see one sign change, and that's it. So I know I'm going to have one positive real zero. I usually don't bother with the negative real zeros just because, I don't know, it seems like more work than is really useful, but some people do. Let's just take a look at what we got. According to Descartes, we'll just make a note of it. I mean, it's not too bad. I'm bad-mouthing poor Descartes. According to Descartes' rule of signs, we will have one positive real zero. And we could do that with minimal work. We just looked, we saw there's a one sign change, there has to be one positive real zero. Now, if I think about the negatives, this part I would do in my head, but I'll just kind of make little notes down here to show you what I'm thinking. So again, I'm thinking about plugging in a negative x. So if I do, anywhere there's an odd exponent, a negative raised to an odd power is going to be negative, so it's going to change the sign of that coefficient. There's an even exponent, a negative raised to an even power will be positive, so you don't change the sign. So it's going to be 81x to the fourth minus 54x cubed minus 27x squared plus 24x minus 4. And I think about the signs. Positive, negative, negative, positive, negative. 1, 2, 3 sign changes. So there's 3 or 1. Remember, look for the number of sign changes. There's 3, and then just keep subtracting 2 until you can't anymore. So there's 3 or 1 negative real zeros. All right, we know we're going to have at least one real zero, is what it's saying. Okay, so that's Descartes' rule of signs. The rational root theorem. Now you guys might have been thinking, man, she's writing down a lot when I was doing this problem up here. All of this stuff. You don't have to write all that down. That was just to show you that all of these are the only possibilities. I wanted you to actually see what they are. Again, normally I would just kind of think of it in my head, but if you are going to write it down, here's a nice, easier way of writing it down. We know that they're going to be plus or minus. The numerators are factors of the constant. What are factors of 4? 1, 2, 4. The denominators have to be factors of the leading coefficient. What are factors of 81? 1, 3, 9, 27, 81. There. Now you got it. That's all you have to do. So now we know any combination that we try for synthetic division, pick a number from here and pick a number from there. So it could be 1 over 1, 1 over 3, 1/9, 1/27, 181. Maybe it's 2 over 1, 2/3, 2/9, 2/27. But just make sure it fits this. Like, I don't see the number 3 in here. I don't see 3 over 1. I see 1/3, but I wouldn't try 3 over 1 because that's not going to work. The other thing, upper and lower bounds, there's no notes to make about that. Just jump right in and just be looking for them. Okay, so now I have an idea. Let's go ahead and set up our synthetic division. Let me double check. 4, 3, 2, 1, 0. I don't need any placeholders when I'm setting up synthetic division. So 81, 54, negative 27, negative 24, negative 4. So I plug in a 1. Bring down the 81. Multiply, add. Multiply, add. Multiply. Now at this point, I can already see this isn't going to work. Remember, in order for this to be a 0, I have to get a remainder of 0. I'm going to get some positive number here, and it's going to be pretty big. When I multiply by 1, it's not going to be enough to... It's going to be too big. In fact, I know I'm going to get a positive number here, and when I add negative 4 to it, it's still going to be positive. That's enough. In fact, if you look, we plugged in a positive, and this bottom row was all non-negative. We found ourselves an upper limit by the upper limit theorem. Again, let's look here. So, if we divide the polynomial by x minus b, where b is a positive number, and we did, b was 1 in our case, using synthetic division, and the row that contains a quotient and remainder, which is the bottom row, has no negative entry, which we didn't, then b is an upper bound. I'm calling it upper limit. It's the same thing. But this means any real zero of this polynomial is going to be less than 1. So although 2 over 1 and 4 over 1 are in my possibilities here, I've just now eliminated them. I'm not going to bother trying them because it's not going to work. And that takes care of all of my possible positives. So let's go to a negative. Let's do whole numbers first. Let's see. Let's try a -1. Okay. So bring it down, and then I multiply by -1, and I add. And then I multiply by -1, and then I add. And then I multiply by -1, and I add. And I multiply by -1, and I add. And it didn't work, but I have just found a lower limit. We just found a lower limit because let's take a look at the wording. The wording up here in the upper and lower bounds theorem, if we look at the lower bounds one, if the bottom row has entries that are alternately non-positive and non-negative. So you have to plug in a negative number, and you have to get the bottom row be alternately non-positive and non-negative. And so let's take a look. We plugged in a negative, and then we had non-negative, and then that's non-positive, and then that's not negative, and then that's not positive, and then that's not negative. So basically look for sign changes, and 0 is like your wild card. So positive, negative, that can count for positive, negative, positive, positive, negative, positive, negative, positive. Yay. So we found a lower limit, so we're not going to try anything less than -1. Well, we can't try anything bigger than 1, can't try anything less than -1. Let's go for fractions then, because that's all that's left. And it may be tempting, let's go for 1/2, but think about that. Does 1/2 make sense? Hopefully you're saying no, because look here. 1/2 does not appear here. 1 over 2, 1 is in the numerator, is in the possibilities for the numerator, but 2 is not in the possibilities for the denominator. I already know 1/2's not going to work. I'm not going to use it. Guess I'll go with 1/3. That is in there. A 1 is in the numerator and a 3 is in the denominator. So that's a possibility. So I go ahead and write all this down again. And bring down the first coefficient. 1/3 of 81 is 27, and we add. 1/3 of 81 is 27, and we add. 1/3 of 0 is 0, and we add. And 1/3 of -24 is -8, and we add. And it didn't work, and this also told us nothing. I plugged in a positive, but this bottom row contains negatives. It's not an upper bound. Oh well. I didn't find anything from this, and that happens. Okay, so let's try -1/3. And so this is how it goes. You're just kind of plugging in and seeing what works. Some people are really good at seeing the numbers and kind of start to see patterns after a few things. Honestly, I'm not one of those people most of the time. I have to just kind of work it out, but I use the upper bound, the lower bound theorem, the rational root theorem to help me kind of narrow down what I'm going to plug in. All right, so -1/3 of 81 is -27, and we add. -1/3 of 27 is -9, and we add. -1/3 of -12, or -36 is 12, and we add. And -1/3 of -12 is +4. Oh, yay! We found one! -1/3 is 0. Ugh, phew! So finally we found a possibility, or we found an answer, not just a possibility. So what have we found? We know that x plus 1/3 is a factor, and that 81x cubed plus 27x squared minus 36x minus 12 is the other factor. Except we have fractions. Wouldn't it be nicer if we had only whole numbers? And the good news is we can get this down to only whole numbers. This will always happen. If you start with all integer coefficients, even if you have a fractional 0, you can still factor this into all integer coefficients. Notice we have a denominator of 3, but also every coefficient in the other factor is divisible by 3. So what we can do is we can factor out a 3 from that second factor here. And then that 3 can distribute into the x plus 1/3, turning it into integers. Yay! So I just took this 3 and distributed it there. And so we got all integers, and we also made these numbers smaller, which is nice, because we're going to have to do synthetic division again. So if we can make the number smaller, it's always nicer. Okay, so now I'm going to set up my synthetic division again. Whoop, 27, 9, negative 12, negative 4. And I always like to, if I find a 0, it doesn't mean it's not going to work again. So once I find one, I'm still going to keep trying it until it doesn't work. And then I know to take it off the list. So let's see here. Negative 1/3 of 27 is negative 9. Add, we get 0. Negative 1/3 of 0 is 0. Add. Negative 1/3 of negative 12 is 4. And then we have, oh, look at that, it did work again. So now we know we still have the 3x plus 1 from before. So don't forget about that. That's important. But now I have an x plus 1/3 and a 27x squared minus 12 for my other factor. And if I do that same trick again, factor out a 3 from here and distribute it into there. So when I distribute, I'm going to get another 3x plus 1. And this would become that. Whoops, it would not become that. It would become that, but then that's just difference of squares. So I have 3x plus 1, another 3x plus 1, 3x minus 2, 3x plus 2, and now I have fully factored that original polynomial without too much work. Let's just kind of look at this again. Remember, this was the original. Here was Descartes' rule of signs. See what I mean? We wrote this down. We didn't even use it, did we? I don't know. We never referred back here. Just kind of use it as you want. It's very useful, though, if you see all positive coefficients, you know there's no positive zeros. So just stick with the negatives. And it kind of makes sense, too. If you have all positive coefficients, the only way to make that a 0, at some point you need some negatives. And if these aren't positive, if these aren't negative, you're going to have to get a negative from here. It kind of makes sense. Otherwise, I don't really use it. But the rational root theorem, very, very handy. It helped us get to the 1/3 fairly quickly, along with the upper and lower bounds. And we just did this. Now, the one biggest complaint I hear students make, synthetic division takes too much space. So I'm just going to show you, I'm going to do the same exact problem, but I'm going to show you a way to show synthetic division where it's a little more space efficient. We can do the exact same work we've done here, and it won't take up nearly as much space. So I'm just going to set it up, and I'll show you how this works. The key to this more space efficient method is we don't care about this middle row of synthetic division. All we care about, obviously, the top row, because that's our original coefficients, and then we just care about the bottom row, and that's it. So that's what we're going to do. So here's the problem again, and I'm going to do the exact same, I'm going to try the same exact numbers, and you're going to see how this works. You still set up your coefficients, 81, 54, negative 27, negative 24, negative 4. And again, if you had any placeholders of zeros that you needed to write, you would put those. Now, I'm going to kind of make a table instead. And I'm going to try 1. So now we're going to do the add and multiply, but we're going to do that middle row in our head. We're still going to bring down the 81, and then you would multiply by 1 and get 81, and then you add to the 54 and you get 135. And then 135 times 1 is 135, plus negative 27 is 108. Multiply 108, add to negative 24, and this where, well, I don't know, it's some big number, but I know I'm going to continue getting positives. That told me I had an upper limit. So it didn't work. Rather than rewriting the whole thing again, I just leave it there, but now I'm going to do a negative 1. Now this is where mentally you're going to have to ignore this row. Don't cross it out though, it still can tell you stuff, just leave it there, just ignore it. Focus on the top row, right above the line. So I'm going to bring down the 81 again. 81 times negative 1 is negative 81. You add to the 54, you get negative 27. Multiply by negative 1 and add, and you're going to get 0. Multiply by negative 1 and add, you're going to get negative 24. Multiply and add, and you're going to get positive 20. Again, we didn't get a 0, but we did have the signs alternate, so, and we plugged in a negative, so we have a lower limit. So I'm not going to try anything besides those, and nothing bigger than 1, nothing less than negative 1. We already know not to try 1/2, so then I went for 1/3. 1/3 of 81 is 27, add, you get 81. 1/3 is 27, add, you get 0. 1/3 of 0 is 0, add, you get negative 24. 1/3 of negative 24 is negative 8, you add, you get negative 12. This told us nothing, so then we tried a negative 1/3, and negative 1/3, excuse me, negative 1/3 of 81 is negative 27, and we add. Negative 1/3 of 27 was negative 9, we add. Negative 1/3 of negative 36 was 12, we add. Negative 1/3 of negative 12 is positive 4, we add, and it worked. Yay! Look at how much less space we took. There's all of this, which was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 lines. And we condensed that down to 1, 2, 3, 4, 5, 6, 7, 8. 8 lines. So much more space efficient to do it this way. Just don't forget, again, we still have the same thing, like we have the, right now, our factor is x plus 1/3. So it won't be until we divide everything here by 3 that we can turn our factor into 3x plus 1. And then you can set it up again. And we tried negative 1/3 again. Negative 1/3 of 27 was negative 9. We add, we get 0. Multiply, you get 0. Add, you get negative 12. Multiply, you get 4. Add, you get 0. So that worked. So x plus 1/3 is our current factor. But if we divide all these coefficients by 3, now we have 3x plus 1 as our other factor. And then at this point we're down to a quadratic. So we know 3x plus 1, 3x plus 1, 9x squared minus 4. Once you're down to a quadratic, you know how to factor those. So, yeah, that's right. Just factor it and boom. So again, I just did the same exact problem we did above, but I was able to fit all of my work comfortably in one screen, whereas up here I have to kind of scroll up and down quite a bit to get it all to all fit. It won't all fit. So to see it all, I have to scroll up and down. So if you're one of those where it's like, the space it's taking up, this is a nice, quicker way to show it. You don't have to, though. Do whatever you're comfortable with. All right, so here's a problem for you guys to try. try factoring it. And this one, let's sketch it. So I'm going to leave this up to you. Give it a shot. We'll take a look at it together. All right, so this is what you should have gotten. You may have started with different numbers than I did. However, there was no sign change in the coefficient. So according to Descartes, we already know there's no positive zeros. So hopefully you didn't choose a positive to begin with. So it made sense just to start with -1, and hey, it worked. But again, like I said, once I find a zero, I like to keep trying it until it doesn't work. So I went ahead and did it again, and it worked again. But at this point, I was down to a quadratic. I could factor that without doing synthetic division. So I found this is what it factored into. And so now I know that those were my zeros. They each had a multiplicity of 2, which is even, which means the graph is going to bounce. As far as end behavior goes, the degree is even, so I think about a parabola that opens up because the leading coefficient is positive. That means it's going to be up on both ends. And so if it's going to bounce at -1 and -3, then the graph is going to look something like that. Here you go. All right, got a couple of other quick things here. This is related to your homework. So one thing, complex zeros will come in conjugate pairs. This is just something to know. So if a plus bi is a 0, a minus bi is automatically a 0. That's all you need to know. So for this example, find a polynomial with integer coefficients that has the zeros of this. Let's go ahead and take a look at what you do. We know that x equals 2/3 is a 0, and x equals 2 minus I is a 0. But remember, we have a complex number here. They're going to come in a conjugate pair. That means if 2 minus I is a 0, 2 plus I is a 0. So we can say 2 plus or minus I. And I'm writing it like that because you're going to see we have a little trick here. Because now I want to find the factors. It does say integer coefficients, so I'm going to have to multiply this all out. That's kind of implying. If x equals 2/3 is a factor, then that means 3x minus 2, or sorry, if x minus 2/3 was a 0, that means that 3x minus 2 was the factor that it came from. To deal with the complex numbers, here's a little trick you can do. I mean, one thing we could do, just so you know, is if x equals 2 minus I was a 0, then x equals 2 plus I is a 0. And if you set each one equal to 0, then you would have those two things. You would have to multiply those together. Ew. I don't want to multiply those. I mean, I'd have to multiply or distribute 3 terms to 3 terms. I mean, it's just tedious. It's not that hard. Ugh. There's an easier way of doing it. That's what I'm going to show you over here. So what you can do is you start with x equals 2 plus or minus I. So that has both zeros in it. I am going to subtract 2. So just get the, get the imaginary part by itself. And then, if you square both sides, squaring x minus 2, that should be easy. You get x squared minus 4x plus 4. If you square a positive or a negative, those signs go away. But I squared is -1. Make that equal 0. And now we have that. Oof. So easier is a fast way to multiply these two zeros together than doing this. However, we still have to go a little further. So we have 3x minus 2 as one factor and x squared minus 4x plus 5 as another factor. Now we got to distribute again. We got to multiply all this out. So I'm going to multiply 3x squared by everything. 3x cubed minus 12x squared plus 15x. Then I distribute the -2 to everything. -2x squared plus 8x minus 10. And then write it in standard form. combining my like terms, and I get this. It's not too bad. But there will be some problems on your homework like that. So just make sure if they gave you a complex zero, make sure that they've given you the conjugate. If they haven't, you need to put it in. And this is just one possibility. I mean, I could multiply by any constant. I could multiply everything by 2. It's still going to give me the same zeros. This is just one possibility. This is the easiest one, though. So you're going to have some a couple of problems like that, 1 or 2 problems like that. And then finally, the last one. There's nothing different than what you've been doing. It's just the wording of the problem. So I actually copied these directions right from the book. Write a polynomial, A, as a product of factors that are irreducible over the rationals, B, as a product of linear and quadratic factors that are irreducible over the reals, and C, in completely factored form. What is it talking about? Well, I see the word factor, I see a polynomial, I can start with that. I'm going to factor. Now, they did tell us one factor. Actually, I'm going to make use of that. If they give you a hint, start with that. However, look at what they gave us. It is not linear. We cannot use synthetic division. We're going to use long division, or polydoku. So we have a 4th degree polynomial divided by a 2nd degree. That means my quotient is going to be a 2nd degree. So I'm going to set up 3 by 3 boxes. I'm going to put my divisor along one box. I do need a placeholder because I'm missing the x term. Remember, if it's a 2nd degree polynomial, there's 3 terms. So my quotient I know is going to be 2nd degree. 4th degree divided by 2nd degree is 2nd degree. So I need 3 terms for that 2nd degree quotient. And then remember how polydoku works. We're going to take the first term of the polynomial of the dividend, put it in here. What do I multiply by x squared to get x to the 4th? I get x squared. I'm going to multiply all the way down then. 0x cubed, negative 6x squared. And then look for those diagonals there. So I have a 0x cubed. I want to get negative 2x cubed. I'm going to need a negative 2x cubed, which means this has to be negative 2x. So then I multiply straight down. Negative 0 x, oops, that's supposed to be cubed. 0x squared, 12x. Look at this diagonal. So I have, when I add so far, I've got negative 6x squared, but I want a negative 3x squared. So I'm going to have a positive 3x squared, which means positive 3 up there. Multiply straight down. And it's good that this last box matched, because I should get a no remainder, because this is a factor. And it all fell kind of into place. These two add up to this like term, so it's all good. So what do we have so far? We have that f of x is equal to x squared minus 6 times x squared minus 2x plus 3. Now let's see, can we factor? Oops, that quadratic right there that we got, are there two numbers that add up to negative 2 but multiply to 3? And there aren't. So this thing will not factor using rational numbers. And this thing will not factor either using rationals. So this is the answer to part A. So what do they mean by part B? Notice part B now says, well, first of all, it says linear and quadratic, which we have. They're both quadratic. But then it says irreducible over the reals. First it was just rationals. Remember, rationals mean whole numbers or fractions, but we can't have things like square roots or imaginary numbers in there. real numbers means we can do square roots now, which means this, if we think of this as difference of squares, we can factor in x minus root 6 and x plus root 6. I'm going to run out of room. I'm going to move this. Then we still have this other factor, though. Actually, the other factor might factor using square roots, so I'll have to take a look at that. But we definitely have this factored now. So for this guy right here, I am going to see what zeros we can get from it, and then see if we can factor from there. I'm going to do the kind of thing like we did up here. If I can find some zeros, then I can find the factor it came from. So let me see what we can do here. I'll do that off to the side. I'm going to see if I can find the zeros for this. Now since a is 1 and b is even, I'm going to use completing the square because it's going to be a lot easier than the quadratic formula. Move the 3 to the other side, and then take half of b and square it. Half of that's -1. Negative 1 squared is +1. Add 1 over here. This is going to factor. This simplifies. We take the square root. We get x minus 1 in the absolute value. Oh, that's a square root of a negative. When I take off the absolute value, I'll have plus or minus I root 2. So x is 1 plus or minus I root 2. That's going to help me for part C, so I've finished it up, but it's an imaginary, and I'm supposed to stay real for part B. So this will not factor anymore. So that's part B. Part A, I kept everything rational. Part B, in order to factor further, I had to involve square roots. They're real, but they're not rational. Part C, if I'm going to use only linear factors, just because of how this guy worked out to be, I have to use complex numbers. So I'm not real anymore. So one of them is x minus 1 minus I root 2. The other one is x minus 1 plus I root 2. And that's all it means. It's weird. One thing I just wanted to let you know, it says completely factored. Honestly, a lot of times this is part A is considered completely factored. Just because this is good enough. If you can get it down to quadratics, even though, we could factor using square roots or imaginary numbers, this is good. This is good enough. But to follow these directions, this is what we wanted. All right, so that's the end. Have fun with your homework. Bye.